All right, everyone. So today we're going to continue to chapter 15. So it's still going to be an inference. So last class we talked about the Z covering interval. We're going to continue on now to Z hypothesis test. Okay. So again, we're doing inferences. We're trying to draw conclusions toward the population. Okay. So learn objective. Understand the difference between the two inference procedures. One is confidence interval, the other is hypothesis test. Confidence interval from last class, where you try to estimate a population parameter, and hypothesis test will be a process to assess a claim about the population parameter, right? You will assess something being true or false. And in all hypothesis tests, we use so-called a 5-step procedure. So please get familiar with the 5-step procedure because we're going to use that 5-step procedure for any of the future hypothesis tests. Okay. And then understand the conditions for Z-test. That'll be the same condition as Z confidence interval. If you recall, we need to have a random sample. Sample size n need to be large enough to apply central limit theorem. And then lastly, we need to know population standard deviation sigma as a parameter. Right? Okay. And then able to perform a Z-test on a practical problem using the 5-step procedure, right? Understand what the p-value represents. This is very critical. We use a probability value to make decisions in hypothesis test to decide if a claim is true or false. What does that p-value represent? Okay. And then able to interpret the results. So basically, after you did a hypothesis test, you either reject the null or fail to reject the null. And either way, you need to interpret what does it mean. Okay. And then lastly, in hypothesis test, we're going to make a decision to say some claim is true or false, but we always have a chance for committing error. We're never going to be 100% sure of whatever we decide in the statistical process. Okay? So you need to understand type 1 error and type 2 error. There are two different types of errors. Okay? So you need to identify in particular practice problem you did after the hypothesis test. Do you have a chance for type 1 error? Or do you have a chance for type 2 error? Okay. All right. And then how do I choose error rate? Okay. We start with, kind of review. There are two different inference procedure. One is confidence interval from last class. We talk about a Z confidence interval in which we're making estimations. And the parameter we're estimating for this class is always population mean, right? And then hypothesis test, we need to assess claim being true or false, right? And we're always going to be interested in population parameter mean. The conditions for the Z-test is exactly the same as Z confidence interval. 3 things: random sample, large enough sample size, make sure central limit theorem will apply, and then lastly, we need to know population standard deviation sigma. Okay. And here it goes very quick. The first animal mentioned in this video will be a cute cat. Okay. And then we have the 5 steps hypothesis testing procedure. Step 1, stating hypothesis. Step 2, state the rejection rule. Step 3, calculating test statistic and find p-value. Step 4, apply rejection rule to make a decision. And step 5, write a conclusion. Basically, the last step is interpret the result. Right? So right now, we're going to start one step at a time. We're going to talk about what we're going to do in each of the steps. Finally, afterwards, we're going to put everything back together to go through a particular, hypothesis test problem. Okay? And this hypothesis testing 5-step procedure doesn't just apply to the z-test we're going to talk about today. It's also going to apply to any hypothesis test procedure in the whole statistical world. Right? So get familiar with the 5-step process. So first step, stating hypothesis. In statistics, we have two different hypotheses. We have null hypothesis. We have alternative hypothesis. Okay? So then what is hypothesis? Hypothesis is the claim that people make about the population. Okay? So then, what's the difference between the null hypothesis and the alternative hypothesis? The null hypothesis is a claim stating something being no effect, no difference, or basically the same. If you're stating something is the same as something else, that's a null hypothesis. And if there is a claim stating something being different, you have different kind of different. It could be larger, or it could be smaller, or simply just different. So you have 3 different scenarios. Okay? But as long as your claim is talking about, the true measures of being different, then that's alternative hypothesis. Okay? So for example, now let's talk about the population. Let's still use all MSU students is our population. So then I'm going to make a claim now. I'm going to claim the average depth of all MSU students is higher than $15,000. Okay? This is a claim about the population, then this will be a hypothesis, right? Then hypothesis, we have 2 different types of hypothesis. We have null hypothesis, we have alternative hypothesis. So what kind of hypothesis is this? Can we tell if this is stating something being the same, or we're stating something being the same, different? So when we look at the keyword, we're saying the average data of MSU students is higher than $15,000, right? So that means we're stating the debt is different from 15,000. So that will be stating something being different. This will be our alternative hypothesis, not null. Right? So the alternative hypothesis, we use a symbol HA represent. So alternative hypothesis, the average debt of all MSU students is higher than $15,000. That's a hypothesis. We can state it that way. Right? And in hypothesis testing, the null hypothesis and the alternative hypothesis will always come the same time. So they both need to be stated in the first step. Okay? So when you state hypothesis, you need to state both null hypothesis and alternative hypothesis. And actually, if you have one hypothesis stated, the other hypothesis will be automatic. So for example, if your alternative hypothesis is the average debt of all MSU students is higher than $15,000, the null hypothesis automatic will be just write everything else the same, the average debt of all NMSU students. Now it will be the same as $15,000. So you can see now this claim is stating something is being the same as something else, right? So this will be our null hypothesis. And that's our first step, stating hypothesis. For any question, identify the claim. That will be our hypothesis. If the claim is stating something being different, that's our alternative hypothesis, HA. If a claim is stating something being the same, that's our null hypothesis, HO. Okay? Good. We don't like to write the long sentence like this. It takes too much time, right? So in writing, we always want to simplify the writing using symbols to note some features. So for example, if we look at our null hypothesis and alternative hypothesis, we most of the time put the null hypothesis on top, alternative hypothesis on the bottom, but it doesn't matter as long as you label them. Make sure you label the hypothesis. So then we know this is our population. All MSU students is our population. Then the average depth of all MSU students, basically this will become a feature that we'll learn about, right? Average of the population. We can use one symbol to indicate the whole phrase, right? Mean, population mean. And it's the same as we can use a sign to indicate that will be equal to, right? And then whatever is equal to, we just write it out, 15,000, right? So we can write our null hypothesis as mu is equal to $15,000. And that means exactly as the whole long sentence. So you can simplify the writing if you use a notation. Okay? And likewise, alternative hypothesis. The whole thing in the front here, average of the population, that's our mean. Higher than will be greater than $15,000. We just write it out as is, right? So then our alternative hypothesis will be mu is greater than $15,000. Right? So that's our first step, stating hypothesis, and that's just like this. Find a claim, write hypothesis. So let's look at a practice. This is the easiest step in some sense, I think. So for example, we have a practice here. We need to identify the null and alternative hypothesis after you read the problem for each of the questions. So the survey of study habits and attitude, SSHA, is a psychological test that measures student study habit and attitude toward school. Score range from 0 to 200. The mean score for college students is about 115, the standard deviation 30. So this is our background information. And the research, interest starting for after, but we have three different scenarios. We have three different researches. First, a teacher suspects the mean score for all their students is higher than 115. So we have a claim being made here, right? The claim is saying the mean score. So basically that means the average score of older students is higher than 115, right? Then this is a claim. It should be our hypothesis. What kind of hypothesis is it? Null or alternative? Is it stating something being the same or different? Apparently it's stating something being different. This would be alternative hypothesis, right? And then the null hypothesis will be basically automatic. you're going to say everything the same. Now it will be yes, the same as 115, right? So that will be our null hypothesis. Then if you write in the symbols, to simplify the writing, alternative hypothesis will be mu, average of all your students, higher than 115, greater than 115. And the null hypothesis will be mu is the same as 115, right? So that's the first step, stating hypothesis, and that's it, right? So likewise, you can state a hypothesis for each of the other two, right? So a teacher thinks the mean score for females is different from 115. Is different from 115, so that claim is stating something being different. That's our alternative hypothesis, right? If you change the different into the same as, that will become our null hypothesis, right? And then for different, we're going to have unequal sign. So average of the female score is different, not equal to 115. And average of female score is the same as, equal to 115. So you have your null and alternative hypothesis stated. Okay? And likewise, if you suspect the mean score for male students is smaller than 115, that's our alternative hypothesis with the smaller than sign. And if you change the smaller than into, I'm sorry, there's a mistake here. This should be the same as here, all right? So we change the smaller than into the same as, that will be our null hypothesis. Then you have an equal sign and a smaller than sign, right? So that's our first step, stating hypothesis. The null hypothesis will always have an equal sign. It's stating something being the same with something else. And the alternative hypothesis, depending on what the claim is, it could have a greater than sign, a smaller than sign, or not equal to sign, right? So that's our first step, stating hypothesis. Okay. So now let's talk about the second step, state rejection rule. All right. So the rejection rule is always stated using one sentence. So always the same sentence for the rejection rule. If p-value is less than a number, then reject the null. So basically, if we reject the null, we are concluding the null is false. On the contrary, then the alternative will be true, right? And if we fail to reject null, then we don't have evidence to say alternative is true, right? Okay. So then, here we have two things. First thing, we need to look at what is p-value. Okay. So p-value is the probability computed assuming that the null hypothesis is true, that the test statistic would take a value as extreme or more extreme than the actually observed. That would be p-value. The smaller p-value, the stronger evidence that the null hypothesis is not true. Okay. So the smaller p-value will lead us to reject the null. Okay. So read the p-value definition for a couple of times. The probability computed assuming that the null hypothesis is true, that the test statistic would take a value as extreme or more extreme than the actually observed values. And that probability is called a p-value. Right, so if you're confused, let's use a small example to explain what this p-value means. So suppose you have a coin, then I'm going to say, I'm going to make a claim. I'm going to claim the coin is a fair coin. So what does it mean it's a fair coin? The coin has two sides, head and tail, right? Then the probability of getting a head will be equal to the probability of getting a tail will be a half, right? So I'm making a claim there. Then that claim will be a hypothesis, right? P equal to 0.5. And what kind of hypothesis is this? Null alternative. If stating something is equal to something else, this will be our null hypothesis, right? And then on the contrary, if we're saying, hey, I don't think the coin is fair, I think it's not fair, then that claim will be alternative hypothesis, right? That means the probability of a head or tail will not equal to 0.5, right? Okay. So then, how do we decide which one is true or false? Now we need to collect some data, right? So we need to do an experiment. We're going to do an experiment that's simple. We're going to flip the coin 10 times. And we're going to record X as number of times it sells head out of 10 times. Okay? So then you understand X could be from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? X could be anything. You can observe any value as X between 0 and 10. Okay? So then, for example, if in scenario 1, we observe X equal to 5, then what's our conclusion? Are we going to say the coin is fair or coin is not fair? Here, we wouldn't have evidence to conclude the coin is not fair, right? So we're going to say the coin is fair. Basically, we're going to say, I think the null hypothesis is true, right? But you could observe other values of X as well, right? What if you observe X equal to 10? What are you going to conclude now? If you flip the coin 10 times and observe 10 heads out of 10 flips, are you still going to believe the coin is fair? I don't think so, right? Now I'm going to say the null hypothesis is false, which means alternative hypothesis will be true, right? So I think the coin is not fair now. But based on what do we make a decision like this? Why do I conclude the coin is fair when you observe X to the 5 versus you compare the coin is not fair when X equal to 10? So a lot of people will say, because it's not likely to happen, right? Right. So that's exactly the idea of what a p-value is. So the p-value is defined as if you assume the null hypothesis is true, if you assume the coin is fair, then how likely are you able to observe an outcome as extreme or more extreme than the outcome you actually observed? If the coin is fair, you're more likely to observe that X equals 5, right? So that probability is big. That's why you believe the coin is fair, the null is true. But if the coin is fair, it's not likely to observe 10 heads out of 10 flips. That probability is very, very small, right? That's what leads us to believe the null hypothesis is false. The coin is not fair. And the probability we talk about in either cases, that probability is referring to as a p-value. Probability of observing something, a sample, as extreme or more extreme than the actual sample you collected. So this is the sample you collected. This is one possible sample. But it's not likely to happen if you assume the null hypothesis is true. If that's the case, we're gonna reject the null by concluding the null is false. Right? So that's what we have. P-value is smaller than something, right? When we have a small probability, we're gonna reject the null. Okay. Then p-value small, we're indicating reject the null, but how small is small, right? So we need to compare p-value with something to see if p-value is small or not, right? Otherwise, we wouldn't know is 0.01 a small p-value or 0.02 is a small p-value. We need to have a standard. And that's what this missing piece is. That will be alpha. We call this as type 1 error. Okay. So basically, we need to manually define how small you want your type 1 error rate to be. So basically, you want to define how small will p-value need to be in order to reject the null. So alpha is also user-defined value. Okay. So you, as a researcher, you need to define what alpha you're going to use for any hypothesis test. But most of the time, we want to have a small alpha, right? Because we want to have a smaller p to reject the null. But how small is small enough? Define the value. The most common used alpha is 0.05. Okay. So then that means 0.05 will be our default value. Just like in common intervals, 95% is the most commonly used values. We use 95% confidence level as the default confidence level in common interval. Then 0.05 will be the default value in hypothesis test or type 1 error rate. Okay. So then we say alpha equal to type 1 error rate. Then what alpha should we use? What values do we use? Even though most commonly used alpha value is 0.05, but doesn't mean you always have to use 0.05. Based on what do we make a decision to pick appropriate type 1 error rate alpha? So now we need to learn about what's type 1 error rate, what's alpha, what does it really represent? Right. So type 1 error is alpha. Okay? So what's type 1 error? So you need to think about the hypothesis test process. Okay? So in hypothesis test, we're going to have a null hypothesis stated. The null hypothesis could be true, it could be false. That's in nature. So anyone make any claim being made, that could be a true claim, it could be a false claim, just depending on how the claim is made, right? At the same time, we are going to make a decision. We're going to decide if the null hypothesis is true or false based on the sample we collect. If we get a different sample, then we're going to make a different decision, right? So we only have two possible decisions to make. One is we're going to reject the null versus we will fail to reject the null. Okay? Then if you reject the null based on the sample information, but the null is actually a true claim, that means you're making a mistake. We call that mistake as type 1 error, and we use alpha represent. Okay? And if you're confused about that, you can always compare to the trial process. Our decision-making process in the hypothesis test is very, very similar to the trial process for, if you've ever been to, the court. If you have a speeding ticket or anything, any kind of trial to go through. The defendant in the trial process, it could be innocent, just dependent on nature. Depending on the nature of the defendant. Did the defendant really commit a crime or not, right? He may be innocent, he may be guilty. That's corresponding to the null hypothesis being true, the null hypothesis being false. But who's going to decide if they're guilty or not? It's not themselves, nature. We need to have some evidence, right? So the evidence, just like the sample, they're going to, get some witnesses, or they're going to check their records, and they're going to, make a decision based on that. The judge will make a decision, either convict the defendant, that means you reject the null hypothesis, or you fail to reject the null hypothesis, means you fail to convict the defendant. So the judge is making a decision in the trial process. We are making a decision in the hypothesis testing process. The judge is making a decision based on the evidence. We are making a decision based on evidence as well. Our evidence is only the sample we collected, right? Okay. Then, if we reject the null and the null hypothesis is true, it will be the same scenario as the judge convicted the defendant when the defendant is actually innocent, right? So we call that as type 1 error. And if we reject the null when null is actually false, that will be the same idea as the judge convicted the defendant when the defendant is actually guilty. So that's a correct decision, right? And next thing, if we fail to reject the null when null is actually true, that's the analogy to the judge failed to convict the victim when the defendant is the judge failed to convict the defendant when the defendant is actually innocent. So that's also the correct decision, right? He's innocent, so we didn't convict him. And the same process as here, but failed to reject null when null is false. That's a correct decision. And then lastly, when you fail to reject the null when null is actually false. It's more like when you fail to convict the defendant, but when the defendant is guilty. The defendant is actually guilty, but the judge let him go. So that's another error, right? But that's a different type of error. We call it type 2 error, and then we use beta represent. So we have type 1 error and the type 2 error. Okay. So then, if you understand what the type 1 error and type 2 error is, now you can help us to pick what type of error we're going to choose, what value of the type of error we choose. So it's always think about what is more important to you when you do your research. So for example, think about the trial process. The type 1 error is the defendant is innocent, but the judge put him in jail, being convicted. That's a bad thing. Type 2 error is the defendant is guilty, but the judge actually let him go free. That's a bad thing as well. They're both bad. They're both errors, mistakes. But which error is more important to you? Do you want to have a smaller chance of type 1 error or a smaller chance of type 2 error? Unfortunately, you can only pick one or the other. If you have a higher type 1 error rate, the type 2 error rate will be smaller. If type 1 error rate will be smaller, type 1 error rate is smaller, type 2 error rate will be bigger. Think about the process. If you want to make sure no one innocent will be put in the prison, then at the same time, you're going to have a higher chance that the guilty people will be, walk free as well, right? So then what type of error is more important? Guilty people walking free versus innocent people being put in jail? What do you pick? It's a hard choice, but we have to pick one, right? And different people may have different decisions. You may have different opinion from someone else of your colleague. Okay. But as a researcher, you have to make a decision. What error do you focus on more? Okay. Another example I can give it to you. So for example, if you're doing a drug study, then okay, so you have null hypothesis, you have alternate hypothesis. The null hypothesis will be the drug is not harming people. Basically, it's not poisonous. And the alternate hypothesis means the drug is harming people. So basically, it is poisonous. Then type 1 error will be when let me read this out. So type 1 error basically is when you reject the null, but the null is actually true. So if you converted that, basically, we are gonna conclude the drug reject null, we're gonna conclude the drug is poisonous. When it is actually not. Reject null, and null is true. This is type 1. And type 2 error will be, we're going to conclude the drug, we failed to reject the null, right? We're going to conclude the drug is not poisonous when it is actually poisonous. So we conclude the drug is not poisonous when it actually is. Then, which one is more important to you? You need to think about the consequence, right? If the drug is poisonous and you conclude it's poisonous when it's actually not, what's going to happen? What's going to be the consequence? The drug is going to be banned from production. It's not going to be sold on the market, right? Then, if you conclude the drug is not poisonous, so it can produce, but what's the consequence when it's actually poisonous? It will harm people, it could kill people, right? So which error is more of a concern? Type 1 or type 2? As a consumer, you would focus on type 2 error, right? Because you don't want to be harmed. But what about the drug company? They're going to be more, interested in the type 1 error, right? They don't want type 1 error because otherwise they're not able to produce, manufacture drug and produce and make money, make profit. So different people will have different opinion. But wherever your position is, you need to make a decision depending on your situation. Right? So type 1 and type 2 error. And if you look at your two type errors, if you are focusing on type 1 error, you want to reduce type 1 error, that's very easy. All you need to do is choose a small alpha. All you need to do is choose a small alpha. So this value, if you're more concerned about type 1 error, make type 1 error small. You can choose alpha equal to 0.01 or 0.001. Right? If you're more concerned about type 2 error, then type 1 error and type 2 error, they are competing with each other, right? So one thing we know is, if we have a bigger alpha, we're going to have a smaller beta, right? That means if you want to have a smaller beta, you want to increase alpha, right? So you can pick a bigger alpha, for example, 10, right? Or 0.15, right? And also, you're also dependent on the consequence. Even if you are more focusing on type 1 error, but should you use 0.01 or 0.05 or 0.001? They depend on the consequence. So for example, if you're doing a drug study like I mentioned earlier, and if you're worried about type 1 error, then you want your error rate to be very, very small because, the consequence is you're going to lose a lot of money for the company, right? Or if you're doing a NASA project, it costs millions and millions of dollars. If you a small mistake, as a type 1 error will cause you losing, all the past effort you have, like millions of dollars being lost. That's a very serious consequence. So you need to have a smaller type 1 error rate, 0.00001, right? But if you're doing a study about a parking space, for example, do we have enough parking lot surrounding a service building? What's the consequence if you committed error? Basically, someone come to the building, couldn't find a parking spot, they're gonna park somewhere else and walk 5 to 10 minutes. But that's not that serious, right? So you can be a little liberal, right? You can choose alpha equal to 0.05 instead of 0.0001, right? So that's type 1 and type 2 error. If we understand this, then we go to our rejection rule. Our rejection rule is always stated like this. If p-value is less than alpha, then reject the null. All we need to change is what alpha we're going to pick. In the class settings, we'll always tell you what alpha to use. If I don't tell you 0.05 is the default, but in your own research, you need to decide what alpha to choose, depending on what kind of study you're working on, right? So that's step 2, stating rejection rule. Right, so we have step 2 done, right? So now we're going to go to step 3, calculating test statistic and find a p-value. Okay. So test statistic is a statistic calculated from the sample, assuming the null hypothesis is true. Right. So then now let's think about if we're doing a z-test. We have a population. And we take a sample with sample size of n. For each sample, we can calculate a sample mean x-bar. Okay? For the population, we're going to have a population mean of mu. If we have a null hypothesis, we're going to have a mu stated as equal to something, right? For example, equal to 115, or any number, or just any number. It's going to be a specific number, right? So, what is p-value defined? P-value is defined as out of all the possible samples of the same sample size, if you draw from the population, you're only going to pick one sample, right? This is the sample you pick. But how likely are you able to see the sample as extreme or more extreme than the sample you collected. So then we need to look at our alternative hypothesis as well. For example, alternative hypothesis will be mu is greater than a number, right? Then if you have a greater than sign here, then p-value will be more extreme, will be even higher, right? So if this x bar is a particular value, for example, 120 for the sample you pick, then your p-value will be probability of x bar as a variable that's as extreme or more extreme is greater than the value you calculated, right? This is your x bar from the sample. This is x bar as a variable out of all the possible samples. Then this is our p-value, right? And how do I find this probability? Probability of x bar related probability. We need to know the distribution of x bar, right? And where do we get distribution of x bar? Central limit theorem, right? From central limit theorem, x bar will follow a normal distribution with mu and sigma over square root of n as parameters, right? Then we just need to do like a normal problem, right? We standardize the event and the probability of x bar minus mu divided by sigma. This is mu, this is mu, this is sigma, right? Greater than or equal to whatever that value x bar is, minus mu divided by sigma, right? And the part variable will be standardized to z, and then here you're going to calculate a z-score, right? So sigma will be given to us. This is sample mean, whatever that sample mean is. Mu is, assuming the null hypothesis is true, you're going to have a mu, and then n and sample size we can, right? So we can calculate that z-score. So this probability will be a p-value, and we can look at it in detail. So we're looking for probability of observing a sample as extreme or more extreme than the sample we collected. We're looking at the x bar as a variable. Okay? Okay, so that's our p-value. Then the test statistic is basically the z statistic we calculated. So the probability of test statistic will be as extreme or more extreme than the statistic we calculated, right? Okay. So then if you think about all the different possible scenarios, then the p-value will be defined as, we just derive this process. This will be p-value, right? If your alternative hypothesis is smaller than sign, the p-value will be this. If your alternative hypothesis is not equal to sign, not equal to sign means it will be either greater than or smaller than, right? Either greater than or smaller than. You can have two tail probability adding up, but because the two probabilities are exactly the same because of the symmetry, we can have a factor of 2 in front, and then we times probability one side. Okay? So we have, different probability as a p-value for z-test. And this z statistic is calculated basically based on our standardization of x bar into z from the derivation we had earlier. Standardize x bar into z because x bar has a normal distribution based on central limit theorem. Okay. So then when you look at the 3 different p-values, if you put into the density curve, the top 2, the p-value comes from one side of the tail, right? So for this kind of hypothesis test, We call them a one-tailed test. And then for the last scenario, the p-value will come from both sides of the density curve, right? So we call this as a two-tailed test. So basically, if you read a research paper and talking about a one-tailed test versus two-tailed test, basically, you're talking about the alternative hypothesis will be either greater than or smaller than sign for one-tailed test, and simply not equal sign for a two-tailed test. Okay. So then, this is our step 3. So we can calculate test statistic and find p-value. The p-value will be found from z-table when you do a z-test. It will be a probability related to z, z-score. And then we are able to find the p-value from step 3, and then we define alpha in step 2, 0.05, 0.01, whatever alpha you choose. In step 4, all we need to do is decide what is the sign goes in between. By the rejection rule, if p is less than alpha, we're going to make one decision, reject the null. If p is actually greater than alpha, then we just fail to reject the null, right? So either way, when you compare p-value from step 3 and alpha in step 2, we're able to make a decision. Either reject the null or fail to reject the null. So that's step 4. Step 4 is very easy. And the last step is conclusion, right? Okay. So conclusion, depending on if you reject the null, then the null is false, alternative true. If you fail to reject null, then we don't have evidence to say alternative true. So basically, either way, you make conclusion about the alternative hypothesis. This is what I recommend you writing as alternative as a conclusion. So we have, if we reject, if we don't reject, right? So if we reject the null, I have to recommend to say we have enough evidence that, and now stating alternative hypothesis is true. So reject null, then alternative true, right? And based on alpha significance level. Significance level is the same as type 1 error rate. So all I need to do is change this sentence into this phrase, alternative hypothesis true, into context words. If you fail to reject the null, basically all you need to do is add we do not. Have enough evidence. So basically exactly the same answer. So this way is very easy. You have the same structure. If you reject the null, then we have enough evidence. If you don't reject null, we don't have enough evidence. And that was it. That's very simple. Okay. So basically, is alternative true or alternative is not true? Right? So that would be the 5-step hypothesis procedure. Okay? So we went through the whole 5 steps. I know this is a lot. This is probably the hardest, concept ever. But once you understand hypothesis testing as well as confidence interval from last class and this class, the rest of the semester is very easy. Basically, very, very similar process with a little picking around for different kind of scenarios, conditions. Right? So make sure you study and understand all the terms we talk about here. So now let's look at an example. This is the scenario we just talked about earlier. The survey of study habits and attitude, SSSTA, is a psychological test that measures students' study habits and attitude towards school. Range score from 0 to 200. The mean score for college students is about 115 and standard deviation 30. So in the first scenario, we're saying a teacher suspects the mean score for older students higher than 115. And basically, this is our claim. We need to assess if that claim is true or false. That means we need to do a hypothesis test, right? So we need to identify this is not a common interval anymore because we're not estimating, we're assessing, right? Then he collected the sample of 25 students, so we added some data in here. With 30 years or older, and the average score is 125.8. And suppose we know the score in the population of older students normally distributed with standard deviation of 30, right? So we're given some information. You need to understand what each of the information is. This will be our sample, right? And what is population? Population will be all of the older students, right? Sample is only the 25 students we choose from there. And then, what is 30? That's population standard deviation sigma, right? So when sigma is given, we need to do a z-test, right? Later on, we're going to talk about when sigma is not given, we need to do a different test. That'll be in the next chapter. And then this is average of the sample. This is x bar, right? Okay. So now let's work on this. We already identified this should be a z-test, right? This will be the first step for any inference problem you work with, determine what procedure to use. Right? So we decided this is a z-test. And then for any hypothesis test, we need to have the 5-step procedure. First step, state hypothesis. Second step, state rejection rule. Step 3, calculate test statistic. And find p-value. Step 4, apply rejection rule to make decisions. And the last step, step 5, you need to interpret the result. You need to write a conclusion. Okay? So we need to go through the 5-step process. First step, stating hypothesis. We have 2 hypotheses, null hypothesis and alternate hypothesis, right? So we talked about how do we state a hypothesis earlier, right? So the mean score for older students higher than 115, that's the claim we're trying to assess. That will be the hypothesis in the problem, right? But what kind of hypothesis is it? It's stating the mean score of the older students higher than 115. It's stating something being different. That will be alternate hypothesis, right? And if I use notation symbols, will be mu is greater than 115, right? And likewise, if you copy everything down, but here, if you're saying it's the same as 115, that will be null hypothesis. In the beginning, I would recommend you to write the wordings and the symbols at the same time so that you can translate from one to the other. You need to know what each of the claim means in the sentence. Once you get used to it, you can just write it with a symbol. That's a lot easier. Right? First step is done. Then second step, state rejection rule. Like we said earlier, rejection rule is always stated as if p-value is less than a number, then reject the null. And this number will be type 1 error rate alpha, right? So in the problem, does it give us what alpha to use? It didn't mention anything, right? But it didn't mention anything doesn't mean it didn't give us, right? We have a default value for alpha, which is 0.05, right? So type 1 error rate default is 0.05. Confidence level default value is 95% for the entire class, right? So that step 2 is done. All you need to change is the value here. And the sign here is always smaller, right? And next step, step 3, we need to calculate test statistic and find p-value. So how do I calculate test statistic? We need to look at the formula of the test statistic calculation, right? So test statistic is right here. Z equal to x bar minus mu divided by sigma over square root of a. Right? So then the test statistic is going to be a z statistic. Let's use a cal here represented. This is a calculated z. So it's differentiating from the variable z in the z table. Then this will be x bar minus mu divided by sigma over square root of n if you copy down the formula. Then we need to put in each of the information here to calculate this, right? So we need to have x bar, we need to have a mu, we need to have sigma, we need to have n. Then let's go back to the question. We know what the sigma is. Sigma is 30, right? X bar is 125.8, and n is 25, right? Sample size n. So n is 25, sigma is 30, x bar is 125.8. So these are what we got from the question. And now we also need to calculate, we also need to find what the mu is, right? So what is mu? How do I find mu? In the problem, it didn't mention mu anywhere, right? Where do we get mu? So the test statistic is calculated by assuming something. We need to assume the null hypothesis, HO, is true. Okay? So if you assume the null hypothesis is true, right here, this is your null hypothesis, right? If you assume it is true, mu equal to 115, right? So then you have everything you need to do the calculation. X bar, 125.8, mu, 115 divided by sigma, 30 divided by square root of n, and is 25, right? And do the calculations. You have 10.8 divided by 30 divided by 5 is 6, right? So that will be 1.8. And we calculated the test statistic. Step 3 is halfway done. Now we need to find p-value, right? So what is p-value then? So we just talked about a p-value definition. P-value will depend on what kind of alternative hypothesis you have, right? When you have a greater than sign, smaller than sign, or not equal sign, the p-value will take different form of z event, right? It doesn't matter which z event we're looking for, we can always look up it from z table, right? So now let's look at what's our p-value. Since our alternative hypothesis here has greater than sign from the earlier PowerPoint slides, we know the p-value will be probability of z greater than calculated z. Basically, the sign here and the sign here need to match. It's easy to remember, right? And the calculated z is 1.8, right? We calculated already. That would be probability of z greater than 1.8. And this is something that you should be already very familiar with, right? That's how we look at on the z table, right? So we need to watch out for signs. Since they have greater than sign, we need to convert it using 1 minus, right? I'm not going to write a middle step, but you need to convert it to be smaller than sign before you go to the z table, right? And then 1.8, if you look it up, 0.9641. So the probability is 0.0359. Right? So step 3 is done. You find the p-value. P-value is 0.0359. So then we go to step 4. Apply rejection rule and make a decision. So now, here is, we have an if, but now we already know what a p is. We already know what alpha is, right? Alpha is 0.05. P is 0.0359. Then what sign goes in between? Greater than, smaller than. That's the only choice we have, right? It's very rarely going to have an equal. Almost never going to have equal, right? So you can have smaller than, right? Because 0.0359 is smaller than 0.05. Then, by the rule, if this is the case, by the rule, we need to reject the null, right? So then step 4 is done. We concluded to reject the null. That means the null is false, alternative is true, right? And now we go to step 5, the last step. We write a conclusion. So we're going to say, follow the format we had earlier. We have enough evidence because we reject the null, right? If we didn't reject null, we're going to say we don't have enough evidence, right? And then after that, you say alternative hypothesis is true. Basically, you put the alternative hypothesis right here, right? Just copy down. We have enough evidence that the average SSHA score of older students is higher than 115. So that's our decision. Yeah, we believe the average SSHA score of the older students is higher than 115. Right? And then this test is done based on 0.05 significance. Right? So we use alpha of 0.05 when we do the hypothesis test. So that's the complete process of performing a z-test using a 5-step hypothesis procedure. Hypothesis test procedure. Okay. Then for any other questions, will be pretty much very similar. So for example, I can go through this very quick. This is the one we just did. And then for the second scenario, we're saying the teacher thinks the mean score of female is different from 115, right? So when you look at that claim, different, that will be not equal to 115, and that will be alternative hypothesis, right? So then the null hypothesis will be mu is equal to 115. So this is first step, stating hypothesis. Second step, state the rejection rule. Reject the null if p is less than 0.05, right? Because alpha is not given to us, so we use 0.05 as alpha. Then step 2 is done. Step 3, calculating test statistic and find p-value. So this is our z-cal. X bar minus mu divided by sigma over square root of n. So if you look at the question, we're going to have x bar is 118.6, right? And sigma equal to 30, and then sample size n equal to 25, right? So then you plugged into the calculation, x bar minus mu divided by sigma over square root of n, so you calculate z-score as 0.6. So now, when you write a p-value is dependent on your alternative hypothesis here, right? If your alternative hypothesis is not equal sign, your p-value will take 2 times probability of z greater than calculated z's absolute value, right? Don't forget you have absolute value sign here, right? So I skip that because 0.6 take absolute value is still 0.6, right? Okay. But when you have a negative z-score, make sure you need to convert it to positive when you have two-tailed test, okay? So p-value is 2 times probability of z greater than 0.6. Then here, basically, you just need to find this probability from z table, probability of z greater than 0.6. When you look it up, 1 minus 0.7257 because they have greater than sign, right? And then outside, you multiply by 2. So you calculate it 0.5486. And step 3 is done. You find p-value. Step 4. So now we're going to compare p-value with alpha. P is 0.5486. That means it's going to be greater than 0.05. And then they go by the rule, since p is not smaller than 0.05, then we cannot reject the null, right? So it failed to reject the null. And then the last step, write the conclusion. So we don't have enough evidence that stating alternative hypothesis in thereafter, right? Alternative 2. The mean score for female students is different from 115. And now we did this at 0.05 significance level. Right? And the next one is very similar. The only difference is you have a smaller than sign alternative hypothesis. So when you write the p-value, you need to have a smaller than sign between the z and the calculated z, right? And then since you have a smaller than sign, when you look up the z table, you look up as this, but everything else is exactly the same. So this is one sample z-test. Right, so here goes our second animal for the attendance points, and here we have a zebra. All right, so let's look at another example real quick when we go through this thoroughly with the 5-step procedure. Recall the 5-step procedure, right? So SAT math score ranges from 200 to 800, and average score nationally is 480. A local high school teacher stated, our high school is ranked pretty high. I think that our average SAT math score should be more than 480. So basically, that's our claim right here, right? The claim is saying the average of all his high school students SAT math need to be higher than 480. So that should be a alternative hypothesis since it's stating something different. And to justify his claim, he collected a simple random sample of 100 students from their high school who had taken the test, and the average score is 495. And suppose the SAT math score for their high school is normally distributed with a standard deviation of 86. Okay? So when you look at the question, we are trying to assess this claim. That means this will be a hypothesis test, right? We only have 2 different types of difference. Hypothesis test, you're assessing claims. Combinable, you're estimating population parameters. Okay? And we're given 86. This will be population standard deviation sigma. So based on that, this is going to be a z-test. Right? So we're going to determine we have a z-test to work with. Right? Then we need to follow the 5-step process. First step, stating hypothesis. Now what's the claim? The claim will be our hypothesis, right? The claim is the average SAT score math for his high school will be more than 480, right? So the average SAT math score of his high school is higher than 480. So then if you write the symbols, a lot easier. Mu is greater than 480, right? So get used to translating from the symbol to the sentence. It's the same thing, just one is like a short notation. And the null hypothesis automatically mu is equal to 480. So first step is done. Second step, if p-value is less than alpha, then reject the null, right? So we need to determine what alpha value to use. So let's look at a problem. Does it give us alpha to use or not? So we are going to do the first one right here. So that means we need to do a hypothesis test with alpha equal to 0.01, right? So then that number 0.01 will be complete over here. Step 2 is done. Restate the rejection rule. Step 3, calculating test statistic and find p-value. The test statistic, we're doing a z-test, so that will be a z-statistic, and it can be calculated from the formula of x bar minus mu divided by sigma over square root of n. Then we need to find each of the measures here. What is x bar? What is mu? What is sigma? And what is n? Right? So then, from here, we can see that 495, this is talking about average of the sample, which is 100 students, is a sample. While the population will be all his high school students, right? It didn't specifically say, but basically it's all high school students. That's our population. Okay. So then this is our sample size n. This is our sample mean x bar. And this is sigma we talked about earlier. Okay. So now if we go back to the process here, x bar 495, mu 480, we need to assume the null hypothesis is true, right? Sigma is 86. 86, right? And there's 100. Right? So then we just plug in all the numbers. X bar 495, mu 480, sigma 86, and 100, and we calculate this, right? So if we calculate, we got 1.74. Then step 3 is calculating test statistic and find p-value. The test statistic is calculated. Now we need to find p-value. So p-value is always a probability in z distribution. And how do we write that event? It will depend on what kind of alternative hypothesis you have, right? Since you have greater than sign, p-value will be probability of z greater than calculated z. And the calculated z is right there, 1.74. So that will be probability of z greater than 1.74. And now this is the z event. Refer to chapter 3, how to look up the z table. We look it up, right? Since you have greater than sign, we need to convert it to be smaller than sign with one subcheck. And then you look at 1.74, you got 0.95 0.91 and do the calculation, 0.040. Right? So the step 3 is done. You find your p-value. Now we go to step 4. So we already defined what a p-value is. We decided to use alpha as 0.01, right? So compare 0.0409 with 0.01. Which one's bigger? Obviously, p is greater than 0.01, right? Then what's our decision? We're gonna fail to reject the null, right? You're only gonna reject null if p is less than alpha, right? If p is greater than alpha, we fail to reject null. And the last step, conclusion. So we say we don't have enough evidence since we didn't reject the null. That, and then bring alternative hypothesis 2 down here, right? That the average SAT math score of all his high school students is higher than 180. And this conclusion is decided based on significance level of 0.01. Significance level. So then this is the whole 5-step of hypothesis. Okay. So then here's a question. Earlier we mentioned that anytime, doesn't matter what decision you're making, you're always going to have a chance to make one or the other type of error, right? We could have either type 1 error or type 2 error. So in this case, what type of error do we have a chance to make? And go back to the type 2 type of errors. Okay. So think about type 1 error is when you reject the null and the null is true. Type 2 error is when you fail to reject null when null is actually false. Right? So basically think about this. If you reject the null, you have 2 possibilities. One is you're going to make a type 1 error. The other is you're being correct, right? And if you fail to reject null, you also have 2 possible outcomes. Either you're being correct or you make a type 2 error, right? So if you look at our process over here, we fail to reject the null, right? If we fail to reject null, that means we have a chance for a type 2 error, right? We're either going to be correct or we make a type 2 error, right? And on the other hand, if you reject null, you can have either being correct or you have a chance for type 1 error, right? So the decision making in hypothesis testing is it's just about using probabilities. So we're going to use the probability to our benefit by, if we do it correctly, doesn't matter what decision you make, either reject null or fail to reject null, you always have a chance for being correct or have a chance for error. But we are able to control the error rate. We can control the type 1 error rate as 0.05. That means if you reject a null every time, you only have 5% of chance to commit an error. On the other hand, you have 95% of chance to be correct, right? And likewise, you can control type 2 error to be small so that the probability of being correct is always a lot higher than the probability of committing error. So it's just about probabilities. That's why we did learn probabilities. Okay, p-value is a probability. Right. So then the last one is basically very similar. We're going to do the hypothesis testing, but now with different alpha value. So if you go through the process, basically the only thing you need to change is the alpha here. And then everything else is still the same. The p-value is still the same, 0.0409. But now when you compare with alpha now, 0.0409 will be smaller than alpha. So we need to reject the null, right? And the conclusion now we're going to say, hey, we have enough evidence to say that the SAT math score for the high school is, higher than 480 at 0.05 significance level. So compare between the two tests we did here with alpha equal to 0.01, we failed to reject the null. With alpha equal to 0.05, we reject the null, right? So picking a correct alpha is critical. Sometimes you're going to get a totally different decision, right? So what alpha should you pick? You're always supposed to pick your alpha before you see your sample. Pick it ahead of time, based on the nature of your study. What type of error is more important to you, type 1 or type 2? Then what is the consequence of committing either type of error? Is it serious or not as a big deal, right? So you choose appropriate alpha. Do not choose alpha after the sample, always before, okay? So that's one sample z-test. Right? So then this is basically, we covered z confidence interval last class and the z-test this class. So that's basically all different kind of inference we have. Either a confidence interval trying to estimate a population parameter, or hypothesis test trying to assess population parameter claim. Right? Then any other inferences we are going to talk about this semester will be pretty much very similar. So make sure you understand the concepts here for confidence interval and hypothesis test before we move on to chapter 18. Right? So that will be it. Thank you for watching, and